An electric car can look complicated. A huge battery underneath, high voltage cables, electronics, one or more motors. But the basic idea is simple. Electricity goes in, the battery stores it, the electronics control it, the motor turns it into motion. That's the whole story. Let's break down what's happening inside the car. Start with the part you can see, the charging equipment. You plug into a box at the home or a station in a parking lot, but here's the key detail. That box isn't necessarily what converts the electricity for the battery.
And this is one of those little details that makes the easy understand the whole EV system. The sink you're plugging into is not necessarily doing all the work.
With AC charging, electricity reaches the car as alternating current. The car's own onboard charging converts it to DC, the form the battery stores. At home, this is relatively slow. A standard US Level 1 connection uses about 120 volts. Level 2 uses high voltage circuit, typically 208-220 volts, depending on the electrical setup, and delivers substantially more power. That's why Level 2 charges much faster. Public fast charging skips a step. With DC fast charging, the AC to DC conversion happens in the charging equipment itself, not the car's onboard charger. The station then feeds DC power to the battery directly under the car's own charging controls, which manage the current and voltage throughout the session. This is one reason the stations deliver far more power than home charging. But the speed isn't about voltage alone. It also depends on the vehicle, the battery, the equipment, the battery temperature, and how full it was.
When you see a charger, advertise it as a ridiculously fast charging. Don't assume that the car will automatically charge it at that number, because the car, battery, temperature, all of these things are get a vote.
Now the part most people picture when they hear electric car, the battery. Think of it as a EV's energy reservoir. It stores the electricity the car will use to move. In many modern EVs, the battery is large, flat pack under the wheel, keeping weight low and using the space between wheels efficiently. Not every EV uses the same layout, but the job is the same: store electrical energy for propulsion.
This is why the battery is such a big deal while shopping EVs. It's not about how far a car can go. The battery size affects the weight, performance, packaging, a huge part of EV's price as well.
A big battery generally stores more energy, but real-world range also depends on how efficiently the car uses the energy. Speed, temperature, and climate control all play a part. Electricity is now stored in the battery, but it doesn't flow straight to the wheels. Something has to control it. That's the power electronics. The key component here is the inverter. The battery supplies DC, but the traction motor in the most EVs runs on AC. The inverter converts and controls that power, so the motor produces the torque and the speed the car needs. It isn't a simple on-off switch. The power is constantly adjusted based on driver input. Press the accelerator harder, get more power. Lift off, and the system changes what the motor is doing. The power electronics act as a traffic controller for energy moving through the drivetrain.
And this is the part easy to miss, because you are not directly controlling the motor by your foot. You are telling the computer you want more, and then the electronic system figure out how to deliver it.
Here's something a conventional car cannot do: regenerative braking. Lift off the accelerator or brake, the motor can work as a generator, not the spinning backward, just reversing its role. Instead of using electricity to turn wheels, the rotating wheels send energy back through the motor into the battery. Not all of braking energy is recovered this way. Friction brakes still do real work, especially in hard stop, but Regen recovers enough to meaningfully extend range and is core part of how EV manage the energy.
And this is one of coolest thing in EVs. When you slow down the car not throwing away the energy as a head, some of it going back to the battery.
Now the part that actually turns the wheels, the electric motor. Compared to gasoline engine, it's surprisingly compact. An EV can use one motor, two, or in some designs even more. Multiple motors let the vehicle drive different wheels independently, improving traction, acceleration, or both.
This is where EVs can get pretty wild. You don't need necessarily huge, powerful motor to get the huge acceleration. Just give the car powerful motor with a very precise control, and then things can get very pretty.
The motor doesn't burn fuel. It takes controlled electrical energy and turns into directly rotation. The motion then has to reach the wheels, which is where the gearbox comes in. And gasoline car might have 6, 8 or 10 speed transmission. Most EVs don't need that. They typically use a single speed reduction gear instead. Why? Electric motors operate effectively across a much wider speed range than a combustion engine, so they don't need multiple ratios to stay in their useful range. One fixed reduction ratio is usually enough. A few performance EVs, like the Porsche Taycan, do use 2-speed gearbox on one motor to balance strong launches with efficient high-speed cruising, but that's exception, not the rule.
So, when people say EVs no gearbox, it's not technically quite right. It actually has, and it's dramatically simpler. And most importantly, you are not sitting there waiting for it to shift through 6 or 8 gears.
The whole system, start to finish. Electricity comes from the grid. The charging system gets into the vehicle. The battery stores it. The power electronics control how it's used. The motor turns into rotation. The reduction gear sends the rotation to the wheels.
And I think it is easy way to understand the difference. An EV didn't remove the complexity, it moved the complexity. You have less mechanical machinery doing the work, and more electronic, battery technology and software controlling it.
Here's the big takeaway. An EV isn't simple because it lacks technology, quite the opposite. It relies on batteries, sensors, software, power electronics and thermal management. But the mechanical path from the stored energy to the wheels is remarkably simple. No combustion, no exhausted system, no engine with hundreds of moving parts, and most EVs no multi-transmission constantly shifting gears. That difference explains a lot about how an wheel feels to drive. A power available almost immediately, smooth acceleration, and drivetrain that's mechanically much simpler than a conventional powertrain. If you forget everything else, remember this. An EV is an energy conversion system. Electricity goes in, the battery stores it, the power electronics control it, the motor turns into motion, the wheels turn.